So good morning all. So last class we have discussed about some demodulators like square law demodulator, square root demodulator, as well as there are two other demodulators are available. One is coherent detection or coherent detector, as well as envelope detector. Those two things we will discuss. If time permits, we will discuss one of the demodulator and its advantages and disadvantages also. So last class we have discussed about the square law demodulator. These relations also we have discussed how to get the modulating signal if I am receiving the AM signal. Okay. So one by one, step by step, we will see how this particular modulated signal is converted into the modulating signal. This derivation is available with you in the last video also, same derivation, but here I have represented in terms of amplitude sensitivity, but the derivation is same. At last we need to extract the modulating signal, which will be the output of LPF, and the output of LPF will decide whether we have recovered the original signal or we need to tune it. Okay, and there are the basic steps what we have discussed in the last class. First, it will enter to a nonlinear device. Then the received AM signal is processed through a nonlinear device, followed by a low pass filter, and then it is followed by a DC blocker. So some of this DC blocker concept will be not given. They will assume that LPF will work to block the DC as well as to provide the modulating signal with other components. Okay. So step by step, once again I will discuss this because few of the students have missed the class. So first, here you can see the received modulated signal is received at the receiver end with some sort of noise, but here noise I am not discussing. I am discussing only the modulated signal, received modulated signal. So once AM signal is received, followed by a nonlinear device, in some of the book it will be written in terms of NLD. NLD means it is a nonlinear device. It can be a diode, it can be a transistor. So depend upon these nonlinear characteristics. So last class we have used a diode followed by a LPF, that is RC circuit, parallel RC circuit, and what is the output of LPF, that also we have seen. But once again I am discussing this with respect to the frequency amplitude sensitivity. So nonlinear device, output of nonlinear device is followed by a low pass filter, and this low pass filter output is called as a modulating signal. Now here it depends upon the characteristics of nonlinear element. So nonlinear element, as we consider that this nonlinear device is a diode, whose characteristics you can see, it is I is equals to A plus dV plus CV square. So these characteristics already we have discussed that with a small sort of potential the maximum current can be drawn. So that is the principle of a nonlinear device. So it is A plus dV plus CV square. Or we can write this equation by suppressing this A. As I have written, I of t is equals to A V1 of t plus V1 square of t. So this, it is in time domain. Continuous reception is there. So since AM signal we have represented in a continuous time function, so my received signal must also be a continuous signal which need to be processed through a nonlinear device. And I am writing that I of t is equals to A V1 of t plus V1 square of t. Now what is this V1? V1 is the received modulated signal. And what is this I of t? I of t is the diode current which we are getting at this particular point. So here I am writing the output of nonlinear device is x of t. It is a time function. So here I have written V1 of t is nothing but an AM signal, received AM signal. So AM signal can be represented in many terms, either in terms of modulation index, either in terms of amplitude sensitivity, or either in a general representation. So here I have written in terms of amplitude sensitivity. You can take this AC inside, this K is equals to 1 by AC will be cancelled out. So it will reveal the general equation, that is AC plus m of t whole into cos omega ct. So this is the AM signal. Now this AM signal is processed through this nonlinear device. Okay. So nonlinear device will substitute in place of V1 of t and V1 square of t as AM signal. So in this I have substituted and I have wrote that output of nonlinear device is x of t. So x of t is equals to A. This is my V1 of t, and this is my V1 square of t. So in place of V1 of t, I have substituted the received AM signal. In place of V1 square of t, just we have to substitute the AM square signal and square it. Next step is what? We need to expand this relation so that the sideband, carrier, modulating signal, harmonic components, everything we can get it in a clear manner. So here I have expanded. Here it is A into AC cos omega ct is multiplied with 1 component will be generated. Another one, A into AC cos omega ct into K m of t is the second component. So you can see that A into AC cos omega ct is the first component. Second is A into AC K m of t cos omega ct is the second component of this expansion. Similarly, this expansion will also reveal some sort of factor. Now since in this equation you can see it is a squaring of this whole term. So B into AC square cos square omega ct, which will be multiplied with 1 plus K m of t whole square. So if you expand this 1 plus K m of t, 3 terms will come. In that 3 terms, B into AC square into cos square omega ct will be multiplied with it. So first component is with respect to 1. So it is B into AC square cos omega ct. Expand this particular part 1 plus K m of t, that is 1 plus K square m square of t plus twice of K m of t. Now simply we have to multiply this component with respect to these 3 terms. So it is expanded. Now it is AC cos omega ct, AC into A K m of t cos omega ct. Similarly AC square B into cos square omega ct. Similarly B into AC square K square m square cos omega square t plus this is the another term. Now you can see this is the presence of carrier, okay, because only carrier frequency is available. Similarly, here modulating signal with carrier is available means sideband is available. So this is the sideband component. Here I can say it is sideband component. This is called my carrier component. Similarly, if you expand this cos square omega ct, you will get one DC component, that is B into AC square by 2, and one harmonic component cos 2 omega ct. So this factor, if you expand it, DC component with harmonic component will be there. Similarly, in this case also m square of t is there, means harmonic component is available as well as cos square omega ct is available. So that means these are this will generate a harmonic component, okay. Similarly, B into AC square cos square omega ct twice of K m of t. Now if you expand this, you will get one term in terms of m of t and one in terms of sideband harmonic component. Now what is the working principle of LPF? The working principle of LPF is it will center to the modulating signal frequency. So whatever the signal is provided at the input of low pass filter, it will only monitor to the modulating frequency component, and it will suppress the rest of the higher component or rest of the carrier component, DC component, sideband component. Only the modulating signal components are going to be taken as output. So here there are 2 steps that follow. First, expand the component. You need to expand this component. Here I have not expanded. You can expand it. You can solve it. You can get a DC component with a modulating signal, and one harmonic component is also available. And output of LPF will depend upon these 2 factors now. It will suppress carrier, it will suppress this sideband, it will suppress this harmonic component, it will present with respect to m square of t, because if you expand cos square omega ct, K square into m square of t is one component, one will be harmonic component. From that, I have generated 2 factors. First, B into AC square, K square, m square of t divided by 2, first with respect to this expansion. Similarly, twice of B AC square K into m of t, this is the second component. So this is the presence of modulating signal. So these are the output of your LPF. So now this particular factor is the output of an LPF, and this is also output of an LPF. Now last class I have discussed that what is the advantage of this particular thing that I have told that I will discuss in the next class. So that advantage I will discuss now, and what is the disadvantage of this particular device, that also we will see. Okay. Now advantage is theoretically it is possible, but practically to synchronize with respect to modulating signal is very difficult. Okay. So why it is difficult, we will see. Now here I have written this phi d into AC square into K m of t. So that means modulating signal is present. This only the amplitude is available. Okay, amplitude is multiplied with the modulating signal. So modulating signal is available. So that is I am saying it is called signal is available. Okay. Similarly, there is another component b into AC square Ka square m square of t. Now this m square of t is the harmonic component. If you expand this m square, you will get some harmonic component. One DC component, one harmonic component. Now that harmonic component act as unwanted signal. Act as unwanted signal means which will hamper to the modulated or which will hamper to the modulating signal. So this whole factor I am saying it is called as noise. Noise means it is an unwanted signal which is the harmonic component of our modulating signal and which will deteriorate the signal quality what we are getting at the output of LP. Now how to judge whether this particular signal recover possibility is higher or recover possibility is less? There is one technique that we will study in our in coming up modules. The term it is called as signal to noise ratio. Signal power divided by noise power. Okay. So signal power divided by noise power. One more important thing, this S by N, it is a ratio. It is basically detected at a receiver end. This S by N, if the value is very greater than 1, it indicates that the signal power is very greater than noise power. If it is greater than 1, then only we can say that the modulating signal can be recovered easily what we have received from a modulated signal. Okay. So if the signal to noise power is very greater than 1, then only the reconstruction of a modulating signal is possible. Okay. But if it is very less than 1, if the S by N ratio, it indicates that the noise power is so much that it will deteriorate the signal power. So if the noise power is so much that means denominator is greater than numerator, definitely the value will come less than 1. So if it is less than 1 means in this sort of case we cannot recover the original modulating signal. It will deteriorate. Okay. So we have to check whether our signal to noise ratio is greater than 1 or it is less than 1. If it is greater than 1, then only we can reconstruct the original signal, and if it is less than 1, then we cannot reconstruct the original message signal. So S by N ratio, if it is greater than 1, that means reconstruction of modulating signal can be done easily. Okay. If your signal to noise ratio is greater than 1, that means signal power is more with respect to the noise power. Then only we can reconstruct the original modulating signal. So this is first. Second case, if signal to noise ratio is less than 1, this indicates that your denominator is greater than numerator. Denominator means noise power. If the noise power is more, I cannot recover the original signal. If this is satisfied, if signal to noise ratio is less than 1, then reconstruction of modulating signal is difficult because the noise power deteriorates the signal power. It will suppress the effect of signal power. So this is the two conditions. This is case 1. and this is case 2. So using these two cases, we can check whether the output of the LPF in modulating signal we can reconstruct properly or not. If the signal to noise ratio is greater than 1, then we can reconstruct the modulating signal. If the signal to noise ratio is less than 1, it is very difficult to reconstruct the modulating signal. Now with the help of this analogy, we will check what is the signal to noise ratio for this square law detector or square law demodulator. So here you can see signal power divided by the noise power. Now as the output of LPF we have seen this is the signal power and this is the noise power. So signal power I will write B into AC square into amplitude sensitivity into M of T whole divided by this is the noise component, harmonic component of modulating signal which will contribute as a noise. So we need to suppress it. But the availability of the component is available here. So it is B into AC square into Ka square into M square of T divided by 2. So this B get cancelled out, AC square get cancelled out. Ka, 1K will be cancelled out, modulating signal 1 and this one get cancelled out. So we will get 2 divided by Ka into M of T. Done? So this indicates that your signal to noise ratio is equals to twice divided by Ka into M of T. Now what is this Ka? This Ka is 1 by AC. Now what is this M of T? M of T divided by AC means modulation index, magnitude of modulating signal divided by AC you will get a modulation index. So here I will write 2 divided by MA. Okay. Now I need to extract the modulating signal. So if I want to extract the modulating signal, what should be the condition? The condition is your signal to noise ratio must be very greater than 1. Done? If it is greater than 1, that means MA must be very less than 2. Because if you take this MA here, you will get MA is less than 2. Now if MA is less than 2 means it can be 0.5, it can be 1, but MA is not greater than 2. So it is less than 2. Now what it indicates? If your MA is less than 2, then what will be the efficiency of a demodulator? That is one more question, because depend upon the efficiency you will decide whether the demodulator working principle is good or not. So how to decide? As we know, efficiency is equals to MA square divided by 2 plus MA square into 100. So in place of MA, let us consider this is 4, this is 2, this is plus 4. I have substituted MA value as 2. So square means it is 4 divided by 6 into 100. So that means it is 2 divided by 3 into 100. So it is 200 divided by 3. So here you will get around 6. This is 18, then 20, 66.66. So this is the 200 divided by 3 into 100. You will get around 0.66 into 100, that is 66.66%. So that means efficiency of this particular demodulator is only 66%. So if it here I have maximum, I have put as a 2. If the modulation index is 1, let us consider. So 1 by 3 into 100. So that means 33.33% efficient. That means this demodulator is no such efficient to recover the original message component. So this is the principle behind which we can decide the demodulator working principle is good or not. For theoretical calculation, it is done. But for practical synchronization of that modulating frequency is very difficult. So the square law demodulator performance is not so good. How we can decide? With the help of this efficiency, with the help of this modulation index. How we have derived this modulation index? We have derived with respect to signal to noise ratio. What is this signal to noise ratio? The output of LPF indicates the presence of modulating signal as well as to its harmonic component. That harmonic component will act as a noise which hampers to the signal quality. So this is the harmonic component and this is my signal. So this I can consider as noise, this I can consider as signal. Now signal to noise ratio is what? If the signal to noise ratio is greater than 1, the reconstruction of modulating signal possibility is higher. But if the signal to noise ratio is less than 1, that means reconstruction is very difficult and the modulating signal won't be recovered as strength as what we are transmitting at the transmitter end. Okay. So here we have considered signal to noise ratio. Then the signal to noise ratio we have derived as 2 divided by k into m of t. This k into m of t is nothing but modulation index. I have substituted. I am analyzing that I can reconstruct the modulating signal. So for reconstruction, signal to noise ratio must be very greater than 1. So here I have used it is very greater than 1. So once it is very greater than 1, that means our modulation index is less than 2. If the modulation index is less than 2, that means it can be 1, it can be 0.5. But maximum if I will take 2, that means my efficiency will become 66. If you consider m is equals to 1, your efficiency will become 33%. That means practical case 33% efficient it is, not more than that. But for practical case we need to recover the original signal in a proper manner. But here what happens? Here the signal quality deteriorates. So the efficiency is 33% or maximum is 66%. But the efficiency must be 100 so that we can recover the original signal. But 100 efficiency is not possible. We can go for 90%, 80% so that we can extract the original signal. So this is the main disadvantage of the square law demodulator. Maximum efficiency it can provide to recover the original modulating signal is that to 66.66% according to this derivation. This derivation is important and these derivations are coming in your exam, in your VTU exam questions also. You can see in previous question paper this sort of analytical questions they are asking. They will not ask directly what is signal to noise ratio or what is the efficiency of this. They will ask on what basis or justify the square law demodulator is inefficient with respect to other. You have to write all these steps. First you have to identify the output of LPF, then you have to check with respect to signal to noise ratio. The signal to noise ratio must be greater than 1. You have to take this factor here, substitute it, identify the modulation index. With the help of modulation index, go for efficiency check. So if the efficiency is 66% or 33%, that means it is not so efficient. The reconstruction of modulating signal is very poor. Okay. So this is the analogy behind square law demodulator. So last class we have discussed about squaring loop also. Squaring loop is also an analytical one, but practically it won't possible. Okay, because the construction of that modulating signal depends upon the low pass filter, and it is very difficult to synchronize that particular frequency. So today we will discuss about coherent detection. And then we will discuss about few problems. And what is the disadvantage of coherent modular detection, that also we will discuss. So next is synchronous detector or detection, or this also we can write it is coherent detector or detection method. Okay, so first I will discuss the transmitter part and how we are extracting at receiver end, that also we will see, and we will analyze with mathematical analysis. So in transmitter part what happens? First, this is the balance modulator. Okay, that we will discuss. So first, modulating signal is provided to the modulator, in which local oscillator will contribute the carrier cos omega c, AC into cos omega c, and then it is passed through a band pass filter through a transmitting antenna. Done. At receiver what happens? This is receiving antenna. Here I am transmitting it, here I am receiving it. Okay. At receiver we have a mixer in which the local oscillator frequency is provided, and then it is followed by an LPS, and then we can extract the modulating signal. Okay. Now synchronous detection or coherent detection, theoretically we can analyze, but practically it is very difficult. It is not possible to synchronize the same carrier frequency what we are going to transmit, because n number, suppose a TV broadcasting unit is there, he is using one carrier frequency to transmit the all message component. Okay, but there are n number of receivers are there, n number of users are there, and those users carrier frequency won't synchronize, because the synchronization means it will synchronize this carrier frequency. This component will be synchronized. If the same carrier frequency we are analyzing at the receiver end and your demodulation is done with respect to the same carrier frequency, then the whole method is called as a synchronous detection method. So for example, if I will use the TV broadcasting what I have told, I am transmitting, there is one transmitter, but there are n number of receivers out there. So when I am transmitting some information with the help of TV broadcasting, I am using a high carrier power, high carrier frequency. But that carrier frequency may not synchronize with the n number of receivers, because the receiver unit is having their own carrier frequency to demodulate. So I can't go for this coherent detection for practical case. It is very difficult to construct or very difficult to synchronize this carrier frequency. If the same carrier frequency is synchronized and demodulation is done, then it is called as a synchronous detection or coherent detection. Okay. So in this block diagram you can see, first part is our transmitter. In this transmitter we are generating the AM signal. Here the AM signal is generated. How? First the modulating signal is passed through a modulator. Either it is a square law modulator, or we will discuss about that balance modulator also. In balance modulator there will be two diodes for positive half and negative half. We have discussed about that square law modulator only with respect to one diode. In balance modulator two diodes will be there. Okay, that we will discuss. So first this modulator in which carrier component is inserted. This carrier component strength is AC cos omega c, and then it is passed through a band pass filter whose output is carrier with side bands. So AM signal is generated. Now here if I will write what is my AM signal, okay, AM signal I can write AC plus m of t cos omega c. Okay. Now if I will take this AC common, I can write 1 plus Ka m of t whole into cos omega c. So this is my AM transmitted signal. Now this AM signal amplitude is this much. This is the amplitude. But what is the frequency component? Cos omega c. Now at receiver section, if the same carrier frequency, if I will synchronize, if I will provide the same carrier frequency at the demodulator part, how we will see? If it is synchronized with respect to transmitter carrier frequency, then it is whole method is called as the synchronous detection. So mathematically we can analyze, we will write mathematical analysis. Mathematical analysis in which this mathematical analysis we are doing at a receiver end. So mathematical analysis at a receiver end. Okay, this is the most important part because detection is done at a receiver end. So first, the received signal is provided to the mixer. Mixer means it is also one sort of modulator. Here the modulator is present. So this modulator acts as a mixer in which the modulating signal and carrier signal both are mixed up and generated pass through a band pass filter. Now here we had a mixer in which the carrier will be multiplied with the received signal. That means let us consider this is the output is y of t. So we need to identify the output of the mixer. First step. Step 1, determining the output of mixer. Okay. Here I am not considering the effect of noise. Simply I am using the AM signal. Later on we can identify the effect of noise also. So output of mixer y of t, which is equals to received signal. What is the received signal? Received signal is AM signal into cos omega c. Into cos omega c. It is simple multiplication of the received signal multiplied. Now we had AM signal as AC 1 plus Ka m of t cos omega ct into cos omega c. Done. So this is the AM signal and this is the carrier frequency which is synchronized for the transmitted carrier frequency. Now here if I will solve, I will get AC plus Ka m of t, and if I will multiply these two factors, I will get cos square omega ct. Expand this component. If you are expanding this component, one component is AC by 2 whole into 1 plus Ka m of t, and another one is AC by 2 1 plus Ka m of t cos 2 omega c. Done. Now this indicate what? It indicate the presence of modulating signal, presence of DC component and presence of harmonic component. If you expand this, cos 2 omega ct into AC by 2 is one component, another one is the sideband with respect to 2 omega c. And here it is AC by 2 and AC by 2 into K into m of t. So when this y of t is passes through LPF, output of LPF. Now what is the working principle of LPF? This LPF is centered to the carrier, is centered to the modulating frequency, and rest of the component like DC component, harmonic component, higher component will be suppressed. So higher component if it is suppressed, let us consider this is our x of t. So output of LPF is x of t. AC by 2 is a DC component, it will suppress. Here I will write AC into Ka into M of t whole divided by 2, because AC by 2 into K into M of t. Modulating signal is there. This is the amplitude part, no need to worry. Next, AC by 2 into cos 2 omega ct, higher frequency component, it is suppressed. Then again AC by 2, K into M of t into cos 2 omega ct, again it is a segment, that is also suppressed. So that means output of LPF is AC Ka divided by 2. Now in place of Ka, if I will substitute 1 by AC, 2 into 1 by AC. So AC will be cancelled out and we will get M of t divided by 2. That means modulating signals we are recovering, same frequency is available but amplitude is reduced by half. So this is the output of synchronous detection method. Synchronous detection method means we are synchronizing the carrier at a transmitter and receiver. Theoretically we can analyze, but practically it is very difficult to design, because the receiver end carrier frequency may not be same what the transmitter end is going to transmit. Example what I have told, a TV broadcast is there, they are using at a certain higher carrier frequency, but we are the user at the day-to-day D2H users are there, so they are accessing the data. Anyhow they are accessing the data, but the carrier frequency which at the receiver what they are using may not be same what the transmitted what the TV broadcast station use the carrier frequency. So it may not be same, because there are n number of users are there, but there is only one transmitter end, and n number of carrier users do not have the same carrier frequency. It is different carrier frequencies are there. So this is only for theoretical analysis it is done, but practically it is not possible. It is only for theoretical calculation. Okay. So this is the working principle of synchronous detection. We need to synchronize this carrier frequency, and then this is the mathematical analysis. Output of the mixer, what happens, followed by a low pass filter, what happens, and the output of low pass filter indicates the presence of modulating signal. It is only for ideal case. Ideals are not practically possible. Practically possible is different demodulation techniques. Okay. Stop कीजिए सर.